Welcome back to JEE Main. In episode 1, we understood what D and F block elements are and why they matter. Today, in episode 2, we go deeper into the electronic configurations of transition elements, the most fundamental part of this chapter. We are not memorizing random configurations. We study them because they help us understand oxidation states, color of ions, magnetic properties, complex formation, catalysis, trends across 3D, 4D, and 5D series. So this topic is the root of everything. Let's start with basics. Electrons fill orbitals according to the Aufbau principle. 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, and so on. Here's the key point. 4's orbital is filled before 3d because 4's is slightly lower in energy in neutral atoms. So for the 3d series, Sc2Zn, electrons fill as 4s superscript 2 3d superscript 1 4s superscript 2 3d superscript 2 4s superscript 2 3d superscript 1. Simple, right? But this is where the exceptions come. These are the most important exceptions for G. Chromium expected 4s superscript 2 3d actual 4s superscript 1 3d. Why? Because half-filled orbitals are more stable. Copper expected 4s superscript 2 3d actual 4s superscript 1 3d superscript 1. Why? Because fully filled orbitals are more stable. This single concept gives to 2-3 MCQs every year. This is extremely important for solving magnetism and electronic configuration of ions. Even though 4s is filled before 3d, it is removed before 3d when forming ions. Example, Fe. 4s superscript 2 3d Fe superscript 2 3d Fe superscript 3 3d. Why? Because in the ion, 3d becomes lower in energy than 4s. This is one of the biggest conceptual points of this chapter. Here is the complete pattern for the 3d series. ScZn configuration format. 4s superscript 2 3d superscript 1 4s superscript 2 3d superscript 2 4s superscript 2 3d superscript 1. Remember only two adjustments. Cr 4s superscript 1 3d Cu 4s superscript 1 3d superscript 1. Everything else is regular. In higher series, the anomalies are smaller than the 3d series. Why? Because heavier elements experience stronger nuclear attraction, better shielding patterns, more uniform energy gaps, hence fewer exceptions. But what is important for G is the effect of lanthanide contraction. Lanthanide contraction causes 4D and 5D elements to have almost similar sizes. This indirectly affects density, oxidation states, color intensity, stability of complexes. We will discuss contraction in detail in a later episode. F block elements fill 4f and 5f orbitals. General patterns. F orbitals start filling after La and Ac. Many irregularities due to close energy levels. F electrons poorly shield. This leads to contraction, color, strong magnetism. Common G takeaway. Lanthanides mostly show +3 oxidation state due to stability of F configurations. Actinides show wide oxidation ranges from +3 to +7. Most common questions involve configurations of ions, stability due to D and D superscript 1, identifying exceptions, which electrons are removed first, predicting magnetic moments based on configuration. Once you master these, half the chapter becomes easy. This was episode 2 of our D and F block elements series. We learned how electrons fill, why exceptions occur, and how to write configurations of ions, the most important foundation for magnetic moment and color. In episode 3, we start one of the biggest portions. General characteristics of transition elements, part 1, where we study oxidation states, radii, density, melting points, and more.